In this video, we're going to look at redox reactions in electrochemistry to do a little bit of AP Chem review. So I'm shown here a standard reduction potential data table, and I have to use this information, and assuming I have a spontaneous galvanic cell, answer a few questions. So before we even do the questions, I need to actually figure out what's my reduction reaction and what's my oxidation half reaction. My data table, if you look at it carefully, both of these reactions are written as reductions. Reduction means gaining electrons, right? So they're both written as reductions. So we need to look at this and figure out, well, only one of them is the reduction. The other half will be the oxidation. So to figure this out, I need to look at this standard cell potential, or this E value. So if I look at my silver reaction, notice that the reduction potential is positive. So that means this is generating energy when you reduce silver. So when you add an electron to the silver ion. So this has to be my reduction, okay, because that's the it spontaneously gets reduced because it's producing that energy. And this occurs at the cathode. Okay, so remember your little acronym, RED, CAT, reduction at the cathode. So as a result, I can tell that my other half reaction, the aluminum half, this has to be the oxidation. And oxidation, remember, occurs at the anode. So remember the acronym ANOX. Again, how do I know that from the data table? Well, right now the aluminum, it's written as a reduction because, again, this is a reduction potential data table. However, if I try to reduce aluminum, the ion, if I try to add electrons to it, notice that the reduction potential is negative. So that means it takes energy to get that reduction to occur for aluminum. Okay, so therefore it does not like to be spontaneously reduced. It will be spontaneously oxidized instead. Now that I know that, I can answer part A, which is to write the Net-Ionic equation, and I should see here it needs to be balanced. So how we do that is we write down our half reactions. Let's start with our oxidation. So the oxidation is the aluminum. Now just be careful, again, over here it's written as a reduction. So I need to flip the equation to show that my electrons are getting lost. So we're going to say aluminum solid produces aluminum 3 plus, or plus 3, the ions, and 3 electrons. Okay, oxidation, loss of electrons. And then for my reduction half, we have to be a little bit careful here because the silver, I don't need to flip the equation because it's written correctly, but I do need to make sure my electrons are balanced. So I can't lose 3 electrons and only gain 1. That doesn't make sense. So I'm going to have to multiply this silver half reaction by 3. And when we do that, we get 3 silver plus 1 ions plus 3 electrons produces 3 silver solids. Okay, now we're going to add up the reduction and oxidation halves. The electrons here are a product in the oxidation half, then they're a reactant in the reduction half. So we're going to cancel these out of our overall reaction. So my reactants will be aluminum solid plus 3 silver ions produces aluminum 3 plus, the ions, plus 3 silver solids. That's my balanced Net-Ionic equation for part A, and that's a very, very common question that does come up a lot on the AP Chem, so it's a good idea to know that strategy and how to tackle a question like that. Okay, let's now do the calculation of the standard cell potential. In part B, there are a couple different formulas for this. I like this version. So standard cell potential is the variable E naught cell that equals E of the cathode, or E naught of the cathode, plus E of the anode. But for the anode, we need to flip the sign here, okay? So flipping the sign is important. Now again, there's a different version of this formula, but I like to use this version based on how my data is given. So the standard cell potential is E of the cathode. So my cathode was the silver half reaction. It's this value up here. Now here's another little tip to be aware of. Although I multiplied the half reaction by 3 to balance it, I do not multiply the reduction potential. So you don't multiply this value by 3. That's because the voltage, it doesn't depend on the amount. So the E of the cathode is still just positive 0.80 volts, okay? Now E of the anode is, okay, here's where we have to be careful again. So the anode is my oxidation. In this chart, this is written like a reduction. So if the aluminum was reduced, then the voltage is negative 1.66 volts. But because I'm oxidizing it and I flipped the equation, that's why I'm flipping the sign here. So when it gets oxidized, it'll be positive 1.66 volts. Hopefully that makes sense. Now the answer, you'll know you're right because if it's a spontaneous galvanic cell, your overall E naught or your standard cell potential, this value has to be a positive number, and that's what we get when we add these up. We get 2.46 volts, and that does represent a spontaneous galvanic cell. Okay, because you have your answer is a positive value there, so you're generating that amount of energy in this redox reaction. Okay, so let's do one more, which says to sketch the galvanic cell. So I kind of made a little skeleton of it already down here. Again, this is sometimes they'll give you a diagram, sometimes you may need to annotate a diagram. So I'm going to put the anode on this side, and we'll put the cathode on this side. And we know that the anode, if we go back to our rough work, it's the aluminum. The aluminum's getting oxidized, so I can call this metal aluminum. And maybe we should write down the half reaction just to review. So this aluminum half reaction is going to be my oxidation, aluminum solid. This will get oxidized into aluminum, the ions, and 3 electrons. So physically what happens is this aluminum metal, it'll actually lose mass. So this will break down or get oxidized into aluminum ions and then electrons, 3 electrons, okay? Now to these electrodes, the anode and cathode, they're also going to be connected by a wire. So we'll sketch that in. And the electrons, they will actually travel up the anode, go across the wire, and then they'll come down the cathode, and then they'll go into this solution where they will be reduced or absorbed or reacted with the ions in there. And so my reduction half reaction was the silver half. Okay, so we're going to say we have 3 silver ions. So again, balanced, plus 3 electrons produces 3 Ag solids. Okay, so we've got silver ions in this solution. And then what happens at the cathode is you will, because you're creating silver, the solid, we say that some of it will plate onto this cathode. So it will, you'll basically create more silver metal, and the mass of the silver will increase. That's another aspect of these galvanic cells. Okay, so that's the anode and the oxidation, the cathode and the reduction, and then one other component of your galvanic cell is you notice you have this salt bridge here, okay? So what is the salt bridge about? It's to help you maintain a charge balance. So if you look at your oxidation beaker where the anode is, because the electrons are leaving there, this side is going to get to positive. So what happens is negative ions from your salt bridge are going to kind of flow into this side, and then the cathode side will get to negative. So positive ions from the salt bridge will get flowed to that side to help keep that charge balance intact. So this is how we tackle a redox problem for Electrochem, and this is a pretty common type of question. If you have any questions about this, let me know, and thank you very much for tuning in.